In this video, I want to do an example of how to find the inverse Laplace transform of a rational function where you have an irreducible quadratic factor in the denominator. And the best way to explain how to do it is to just look at an example. So find the inverse Laplace transform of 2s squared plus 10s all over s squared minus 2s plus 5 times s plus 1. So I look at this, I'm trying to find the inverse Laplace transform of this. And I look at the denominator, s squared minus 2s plus 5. Does that have any real solutions? If you set that equal to 0, do you get any real roots? No. One way to see it is to use the discriminant. If you look at the discriminant of this quadratic, that's b squared minus 4ac. So this quadratic has discriminant. Well, in general, it's b squared minus 4ac, and in that case, it's going to be negative 2 squared minus 4 times 1 times 5, and that's 4 minus 20 is negative 16, and that's negative. And if you have a quadratic with negative discriminant, it has no real roots. So this quadratic is not factorable over the real numbers. In other words, it's irreducible. That's another word for it. So it's irreducible. Okay. And when you have an irreducible quadratic, you're going to use partial fractions. So you have this partial fraction decomposition. I have an irreducible quadratic factor and then a linear factor. So the first step is to use partial fractions decomposition of this, which we know how to do. And let's just check that the degree of the numerator, before we do the partial fractions, that the degree of the numerator is less than the degree of the denominator. Well, that's true, because the denominator has degree 3, and the numerator has degree 2. And remember, we know that the denominator has degree 3, because if you multiply the highest power terms, s squared and s, you get s cubed. That's degree 3. Okay, so you do partial fractions to this. I have a video where I actually did the partial fraction decomposition of this. It's the video where I talk about partial fraction decomposition. And if you do the partial fraction decomposition, you are going to get 2s squared plus 10s over s squared minus 2s plus 5 times s plus 1 is equal to negative 1 over s plus 1 plus 3s plus 5 over s squared minus 2s plus 5. Okay, so pretty standard partial fraction decomposition. And I just want to remind you, why do we check that this quadratic is irreducible? Because if you could factor it over the real numbers, then you would actually have distinct linear factors, and then your partial fraction decomposition would be different, right? So if it was possible to factor this, maybe it was possible to factor the quadratic, but you just didn't see how to factor it. Well, that polynomial you could still factor, and then your partial fraction decomposition would be different. Okay. But here we saw that since the discriminant is negative, you really can't factor it over the real numbers. Okay. So you have this. Now we need the inverse Laplace transform of this. Well, we know the inverse Laplace transform of that. Remember, when you have a sum, you can find the inverse Laplace transform of each thing. We know the inverse Laplace transform of negative 1 over s plus 1, that has Laplace transform, inverse Laplace transform e to the minus t. Okay, that's the Laplace transform e to the minus t. Laplace transform of e to the minus t. But the question is, what is the inverse Laplace transform of this part? 3s plus 5 over s squared minus 2s plus 5. Now we know, so the question is, how do you find the inverse Laplace transform of functions that look like this, where you have a linear over a quadratic? Okay. So we know how to complete the square of the denominator. Okay, I have a video where I go over how to complete the square. Now, if you're taking differential equations, you might not remember how to complete the square, but it's very standard. So let's just review what you do. So what you're going to do with this s squared minus 2s plus 5, okay, this s squared minus 2s part, let's just pay attention to that. Completing the square means you take this and then you add a constant so that you get something squared. And what you can do with s squared minus 2s is you can take half of the coefficient of b and then square it. So if you take half of negative 2, you get negative 1. And then if you square it, you get, so if you square this, you get negative 1 squared is 1. So if you add 1, you will be able to write this as a perfect square. And in fact, this does factor as s plus 1 in parentheses squared. So this is going to be, I can write this as s squared minus 2s plus 1 plus 4. And this part, this s squared minus 2s plus 1, is s plus 1 in parentheses squared. So I have s plus 1 in parentheses squared plus 4. So I'm writing that. Now I'm writing that because I know that I know from my partial fractions, my inverse Laplace transform, I know how to find the inverse Laplace transform if I have something that's like s minus a over s minus a squared plus, squared plus b squared, and if I have b over s minus a squared plus b squared. I know how to find the inverse Laplace transform of those things from the table. So I'm trying to make terms that look like where I'll get these expressions. Right now, I don't have that. I have 3s plus 5 over this quadratic, which is completely multiplied out. So what I'm going to do with this 3s plus 5 over s squared plus, s squared minus 2s plus 5, first you rewrite this, you write the denominator so that it has this form, s minus a squared plus b squared. Right? And that's what we just did. We started out with the s squared minus 2s plus 5, and we wrote it like this. So it's s plus 1 squared plus 4. And this is, this s plus 1 is s minus negative 1. Okay. Now we need, in the numerator, we need things like s minus a, so that's s plus 1, and we need b. Well, b is 2 in this case, right? Because this is 4 equals 2 squared. So I have a is negative 1, b is 2. So I'm trying to rewrite the numerator, and in my numerator, I want, 3s plus 5. I want an s minus a. I want an s plus 1. Okay. So I want a constant times s plus 1 plus another constant. Now what constants are going to work? Well, I want, again, we use this fact that we want the coefficients to match. This number here, can you figure out what number has to go there in order for the right-hand side and the left-hand side to match? This has to be 3. And the reason it has to be a 3 is because when I distribute the 3, I need to get a 3s. Because I need a 3s here. I'm not going to get, here I have a constant, so I'm not going to get any s's. So that's why this first number has to be 3. Now what am I going to get for this other constant? Oh, sorry, this should be a minus. Oh, that's a minus. Okay, sorry. My a is positive 1. Uh-oh. Okay. Well, I should still get 3. So now what's my other constant going to be? I need 8, right? Because I get, maybe I'll just write this like s minus 1, and then I need plus 8, because I want to get 3s plus 5, and I'm going to get 3s minus 3 plus 8 is 3s plus 5. So now that I have that, I can rewrite the numerator as this. This thing is the same as this thing. So I'm going to rewrite that here. So I'm going to get 3 times s minus 1 plus 8 over, oh, that's a minus, s minus 1 squared plus 4. Now I'm going to split this fraction up into 3 times s minus 1 over s minus 1 squared plus 4 plus 8 over s minus 1 squared plus 4. Now you see that we do have this s minus a over s minus a squared plus b squared. We have it here. So we can take the inverse Laplace transform. We can take for the other thing, we can take the inverse Laplace transform if we had this. Now here, this 8 over s minus 1 squared plus 4, my b is 2. So what I want is a 2 on the top, not an 8. So what can I do with that? How can I rewrite this expression with the 8 on the top so that I get a 2 on the top? I can write as 4 times 2. So it's going to be 3 times s minus 1 over s minus 1 squared plus 4 plus 4 times 2 over s minus 1 squared plus 4. And now I can find the inverse Laplace transform of this. So my f of t is going to be, well, remember we had that negative 1 over s plus 1. And the inverse Laplace transform of that was e to the minus t. So we have a negative because we had a negative 1 over s plus 1. Okay, negative e to the minus t, and then plus 3 times e to the t times cosine of 2t, and then plus 4 times e to the t times sine of 2t. And we're using the inverse Laplace transform table to do that. And that's how you do it. So let's just review what we did. So when you have this inverse Laplace transform problem with the irreducible quadratic and a linear term, well, it's just in general when you have an irreducible quadratic. You don't necessarily have to have that linear term s plus 1. Now this irreducible quadratic, when you do partial fractions, you're going to get a linear term over a quadratic term, like this 3s plus 5 over this quadratic irreducible term. And the idea is that you know how to do the inverse Laplace transform when you have things like this, s minus a over s minus a squared plus b squared, b over s minus a squared plus b squared. So you want to write it in terms of those so that you can do the inverse Laplace transform. And so first you rewrite this using partial fractions. You write the denominator using completing the square. Using completing the square. And once you complete the square, then you need to rearrange the numerator just by figuring out what the coefficients have to be, right? So you think about, okay, if you had like s minus a and a number plus another number, what's going to match it with what you have? And then you figure out what the numbers are going to be. In this case, it was 3 and 8. And then once you have that, you split it up like this. And then you might have to, because you want the numerator to match exactly, you might have to pull out a constant in front. So for this 3 times s minus 1, I needed the 3 out so that I had an s minus 1 on the top. And then for the other one, I had an 8 over s minus 1 squared plus 4. I need to write it as 4 times 2 because I wanted a 2 on the top. And once you do that, then you can find the inverse Laplace transform. Okay, thanks.